Just imagine the situation of an emergency department in a hospital. Most of the time, it is overcrowded with long queues of patients. Have you ever thought about how much time a patient needs to wait to be attended by the doctor? As the patient is already in an emergency, it means pain or discomfort, even a second counts to him. Is there any way we can reduce this waiting time? Think about another situation where you are in the queue of an ATM to withdraw the money. And you are thinking, how long will it take for your turn to come? These answers can be sought by queuing theory. Hello everyone. Welcome to the lecture series on health management. We discussed that management methods and techniques are broadly classified into 5 categories: statistical techniques, activity analysis, mathematical techniques, financial techniques, and others or miscellaneous techniques. Activity analysis includes techniques like time motion studies, work sampling and activity analysis, queuing theory, and Gantt chart and work schedule. In this session, we will discuss the queuing theory. First, let us understand the queuing theory. Queuing theory is the mathematical study of the formation, function, and congestion of waiting lines or queues. It is also referred to as queue theory or waiting line theory. Before going into the technicalities of the queuing theory, let us discuss a few terms. Queue is an aggregation of persons or items waiting for a service function. Queuing is a process where people, materials or information must wait for a particular time to get a service. Basically, queuing means congestion or crowd. Customer, someone who requests a service and waiting in the queue. Arrival, the procedure for getting customers to the queue. This is the input part of the system. Server, someone or something that delivers the services is referred to as the server. System, this includes both waiting lines or queues and service functions. There are 6 terminologies which are important to understand in queuing theory. Arrival pattern, service mechanism or service pattern, queue discipline, capacity of the system, customer's behavior, and population. Number 1, arrival pattern. The arrival pattern of customers may be random or fixed. For example, suppose customers arrive at a fixed time interval, like one customer every 2 minutes. In that case, it is called a fixed arrival rate. But practically, it does not happen. The customers arrive at random intervals, which means there is no fixed interval between arrival of 2 customers. When the arrival pattern is random, it follows some probability distribution. The most common distribution followed is the Poisson distribution. The Poisson distribution is a discrete probability distribution that measures the probability of a given number of events happening in a specified time period. The arrival of one customer is independent of the arrival of other customers. We calculate 3 parameters in the arrival pattern. Arrival rate. Arrival rate is the number of customers arriving per unit of time, which may be per second, per minute or per hour. Variations in arrival rate can occur at different times of the day or on different days of the week or month. For example, a food outlet knows that on Saturday evenings between 7 p.m. and 11 p.m., the arrival rate of customers is very high. Hence, they require more personnel than on other days. Mean arrival rate. It is the average number of customers arriving per unit of time. It is denoted by the Greek letter lambda. For example, if an average of 3 customers arrive every 5 minutes, the mean arrival rate would be 3 by 5. Mean time between arrivals. It is the average time interval between 2 customers. It is denoted by 1 upon lambda. In the above example, the mean time between arrivals would be 5/3. Number 2, service mechanism or service pattern. The ability of the servers to serve the customers will determine the system's performance. The faster the server is able to serve, the better the system performance. We can say that the arrival pattern is the demand side of the system, and the service mechanism is the supply side of the system. To determine the service mechanism, we need two main parameters, the number of servers and the number of queues. Each parameter can take two values, single or multi. So, there may be four possible combinations. Single queue, single server. This model has only one queue and one server at the end. As soon as a customer is attended to, they receive full service. For example, an automated car wash. Number 2, single queue, multi-server. This model has one queue, but the number of servers will be 2 or more. These multiple servers may be parallel or in series. A customer need not to go to all servers if they are parallel. For example, waiting line at the airport for check-in. It has one queue but multiple parallel servers at the end. But, if the servers are in series, the customer will have to go to all the servers to get the full service. For example, the admission process in the school, where the first counter is for filling out the form and the second in the sequence is to deposit the tuition fee. Number 3, multi-queue single server. This pattern has several queues but only one server at the end. For example, an airline ticket counter with separate queues for business class and economy class passengers, but one server at the end. Or, separate lines for males or females at one ticket window. Number 4, multi-queue multi-server. This pattern has several queues and several servers at the end. For example, a laundromat with several washers and dryers. Or multiple billing counters at a grocery store. We calculate three parameters in the service mechanism or service pattern. Service rate. Service rate is the number of customers served per unit of time, which may be per second, per minute or per hour. Mean service rate. It is the average number of customers served per unit of time. It is denoted by the Greek letter mu. For example, if an average of 2 customers are served every 5 minutes, then the mean service rate would be 2/5. Mean service time. It is the average time interval between serving 2 customers. It is denoted by 1 upon mu. In the above example, the mean service time would be 5/2. The service time also follows the probability distribution. The most common distribution followed in the service time is exponential distribution. Number 3, service discipline or queue discipline. This gives the value by which customers to be served are selected. The service discipline may be different types. Number 1, first in first out or FIFO or first come first served. This is the most popular service discipline. It maintains fairness among customers. For example, queue at ATM or at a grocery shop. Number 2, last in first out or LIFO or last come first served. It is not a common discipline. For example, goods inside a delivery truck are usually arranged such that the first item entering the truck will be delivered last. Number 3, priority selection discipline. This discipline is also applied in many places. For example, business class passengers will enter the aeroplane first before the economic class. A classic example of priority selection is the emergency department at a hospital. Patients are served according to the severity of their illness rather than on a first-come first-served basis. It demands adding a service step called triage, in which a nurse assesses each patient's emergency severity to determine whether that patient should be given priority to be served. Another example is the express lane in a grocery shop, allocated for people buying only a few items to check out more quickly rather than waiting in line behind other customers with full carts. This way, the customer's satisfaction is improved. Number 4. Service in random order or SIRO. In this discipline, there is no fixed pattern to provide the service. Customers are selected for service at random, irrespective of their arrival in the service system. In this, every customer in the queue is equally likely to be selected. Number 4. Capacity of the system. This is the maximum number of customers that can be incorporated or allowed in the system. It can be either finite or infinite. In finite capacity, the system can incorporate a limited number of customers in the system. For example, a fixed number of appointments offered by a clinician in a day. While in an infinite capacity, there is no limit to the system for incorporating the customers into it. For example, a waiting line in front of an ATM can be of infinite length. Number 5. Customers' behavior. Based on the existence of a waiting line, we can categorize a queuing system into two types: bulk queue and waiting line queue. The bulk queue is a queuing system where the customers do not form a waiting line. The system requires minimal space, but the order of the queuing discipline is unclear or random. Bulk queues tend to be disorganized. A waiting line queue is a queuing system where the customers form a proper waiting line. The behavior of the people in the waiting line queue may have different connotations, such as balking, a situation where a customer does not join the queue at all because either the queue is too long and he does not want to wait or there is not sufficient waiting space. For example, at the railway station ticket counter, where there usually are long lines to buy tickets. So, the customer decides not to join the line at all. Reneging, it is a situation whereby a customer joins the queue, but due to impatience, he decides to leave the service completely. For example, at the billing counter in a supermarket, people get impatient waiting in line to check out, so many times, people leave the baskets and just walk out without buying anything. Jockeying, it is a situation in which a particular customer moves back and forth among different queues, seeking for the fastest moving queue. This can be seen typically in supermarkets and train stations, where a person leaves the line he is standing in, and joins another line which appears to be shorter or appears to be moving faster. Collusion, this is a behavior in which customers cooperate with each other, and only one of them may stand in the queue. For example, while buying a movie ticket, one person can collect money from many and stand alone in the queue for all of them to buy their tickets. Number 6. The calling population. The population of potential customers is referred to as the calling population. It is usually assumed to be infinite, even though the number of potential customers is actually finite. How the queuing theory evolved. Let us discuss about the historical background of the queuing theory. In the early 20th century, there was a Danish mathematician and engineer, Agner Kraarup Erlang. Erlang worked for the Copenhagen Telephone Exchange. He wanted to analyze and optimize the operations of the telephone exchange. He sought to determine how many circuits were needed to provide an acceptable level of telephone service for people not to be on hold or in a telephone queue for too long. He was also curious to find out how many telephone operators were needed to process a given volume of calls. The first paper on queuing theory was The Theory of Probabilities in Telephone Conversations, published in 1909. His mathematical analysis was concluded in his paper, Telephone Waiting Times, published in 1920. He proposed some of the first queuing models in the paper and laid the foundation of applied queuing theory. The international unit of telephone traffic is called the Erlang in his honor. The question is, why queuing theory is important? Waiting in line is a common occurrence in everyday life. Let us recall a typical situation of our everyday life. I woke up early and found that the toilet was occupied by one of my family members. When I started moving to my office, I faced traffic congestion on the road. To fill the petrol in the car, I had to wait in the queue at the petrol bunk. I went to the bank today, and again, I had to be in a queue to get my own money. In the office, I queued in front of the elevator. In my office, my documents need to queue to be printed in a shared printer. In the afternoon, I ate in the canteen, again I had to wait for my food. While returning home again, I had to face traffic congestion on the road. I went home exhaustively, and while sleeping, I felt that my productivity was low due to so much queuing in my everyday life. We know that time is irreversible, and it is the most precious resource. Queuing is one of the greatest sources of time waste and inefficiency in our lives. It hinders our productivity. But, at the same time, bad things happen if there is no queuing process to deal with overcapacity. For example, suppose a website has too many visitors. In that case, it will slow down and fail if it does not include a mechanism to adjust the speed according to the queue of visitors. So, it is important to learn how to solve queuing problems. Queues are a way of dealing with the imbalance between supply and demand. Queuing theory helps to describe queue characteristics such as average wait time and gives tools for queue optimization. Queuing theory helps in designing efficient and cost-effective workflow systems. Queuing theory also helps businesses by improving the satisfaction of customers and employees. A question comes to mind: where can the queuing theory be applied? Queuing theory can be applied in any field or discipline, including telecommunications, transportation, logistics, finance, emergency services, computing, industrial engineering, project management, and operations research. Now let us discuss the operating characteristics of the queuing system. There are 5 operating characteristics of the queuing system. Number 1, queue length. This is the average number of customers waiting in the queue. This is denoted by the symbol LQ. Number 2, system length. This is the average number of customers waiting in the system, which means the number of customers in the queue plus the number of customers in the server. This is denoted by the symbol LS. Number 3, waiting time in queue. This is the average time spent by a customer in the queue before being served. This is denoted by the symbol WQ. Number 4, waiting time in the system. It is the average total time spent by a customer in the system. That means waiting time in queue plus the service time. This is denoted by the symbol WS. Number 5, utilization factor. This is the degree of utilization of the system. It is also called traffic intensity. It is denoted by the symbol ρ. It is calculated by dividing the mean arrival rate of the customers by the mean service rate. So, the formula for a single server will be ρ equal to lambda divided by mu. This formula is for a single server. If there are multiple servers, ρ is equal to lambda divided by c, mu. Here, c is the total number of the servers. For example, if in a single-channel queuing model, the mean customer arrival rate is 12 per hour, and the mean serving rate is 24 per hour. What will be the utilization factor of the system? After putting the values in the formula, the utilization factor would be 12 divided by 24, which is 0.5. That means the utilization of the system is only 50%. The utilization factor should be equal to or less than 1. If it is more than 1, that means the customers are arriving faster than they can be served, and the system is overburdened, so the line will grow without bounds. If the ratio is less than 1, that means the waiting line will reach a steady state. There are two states of the queuing system: transient state and steady state. The transient state of a queuing system is the state where the probability of the number of customers in the system depends upon time. Let Pn, t, indicate the probability of having n customers in the system at time t. Then, if Pn, t, depends upon t, the queuing system is said to be in the transient state. The steady state of a queuing system is the state where the probability of the number of customers in the system is independent of time. The transient state comes first. After the questing system becomes operative for some time, the probability of the number of customers may become independent of time, and at this point, it is known as steady state. That means the probability Pn, t, may become independent of t. In reality, initially, the system starts with empty and idle conditions. For example, a shop opened in the early morning with no customers yet. Then it gradually goes into one or more peak time where the number of customers in the system reach the highest level and then gradually reduces. At the end of the service hour, say, the night before closing the shop, there are no more customers. Thus, the assumption of a steady state in the queuing theory does not represent a true reality. Let us understand Little's theorem about queuing theory. Massachusetts Institute of Technology professor John Little developed Little's law in 1954. Little's theorem can be written like L is equal to lambda multiplied by W, where L is the average number of customers in a queuing system. This variable is also called work-in-progress items or WIP. Lambda is the average arrival rate, also known as the throughput. And W is the average time a customer spends in a queuing system. In project management, it's referred to as lead time. So, this theorem states that the average number of customers in a stationary queuing system equals the average arrival rate multiplied by the average time a customer spends in the system. It can also be written as WIP equal to throughput multiplied by lead time. The relationship is not influenced by the arrival process distribution, the service distribution, the service order, or practically anything else. In most queuing systems, service time is the bottleneck that creates the queue. Imagine a small clinic with only one doctor. The system will be like entrance, registration, consultation by the doctor, and then exit. If the rate at which the patients enter the clinic means the arrival rate is equal to the rate at which they exit, the system will be stable. But, if the arrival rate exceeds the exit rate, it will become an unstable system, where the number of patients waiting in the clinic would gradually increase towards infinity. If you want to use Little's law, remember that you must have a steady state condition where the variables are unchanging in time. Suppose the arrival rate of the patients is 10 per hour, and they stay in the system for an average of half an hour. How many patients will be in the queue at any point in time? Here, lambda is 10 and W is 0.5. So, the L will be 10 multiplied by 0.5, which comes out to be 5. This means there would be 5 patients in the clinic at any time. Suppose the doctor has become more famous, and the arrival rate has increased to 20 patients per hour. and they stay in the system for the same time, which means an average of half an hour. So, the L will be 20 multiplied by 0.5, which is equal to 10. Now, there would be 10 patients in the clinic at any time. In this situation, the clinic needs to work on the available seating capacity in the waiting area or think about increasing the number of servers, which means doctors. Cardi Technomo has proposed a very simple formula to calculate the number of parallel servers required in a queuing system. This is S is greater than or equal to the N multiplied by T and divided by T. Here, S is the number of parallel servers. N is the total number of customers or population if it is finite. T is the average time a customer spends in a queuing system, and T is the maximum time to finish the queue. For example, in a conference lunch, suppose each participant needs about 120 seconds to take their food, and there are 1,000 participants. If the lunch break is for 1 hour, how many tables should you arrange? Here, N is 1,000. T is 120 seconds. And T is 1 hour means 3,600 seconds. Let us put everything into the formula. It comes out to be 34. So, you need to arrange a minimum of 34 tables to serve the food to all participants within 1 hour. Let us take another example. A school started registration and tuition fee payment of students. One working day is from 9 a.m. to 5 p.m., including 1 hour of lunch break. Each parent needs about 60 seconds to be served by all the serial servers. Then how many days will be required to register 10,000 students? Here N is 10,000. T is 60 seconds. Servers are open for 7 hours per day, excluding 1 hour lunch break, which means 7 times 3,600 is equal to 25,200 seconds per day. So, T is 25,200. Let us put everything into the formula. It comes out to be 24. So, it will take 24 days to register all 10,000 students if only one set of serial servers is used. This formula only gives you a rough approximation. However, its simplicity is very handy for computing the need for the number of servers without the need to understand the concept of probability. Now, let us discuss the classification of queuing systems. In 1953, David George Kendall suggested a notation that is helpful in classifying a wide variety of different waiting lines. These are called Kendall's notation. The simplest form of Kendall's notation consists of 3 letters, A, B and C. It is represented as A/B/C, where A represents the probability distribution of customers' arrival. B represents the probability distribution of service time. And C is the number of servers. Later on, other letters were added to this, and it was modified like this. Here, D is the maximum number of customers allowed in the system or the capacity of the system. And E represents the queue discipline. Different letters and symbols are used for these alphabets. Commonly used letters in position of A or B are. The symbol M represents Markovian. It is to indicate the Poisson process, which means Poisson distribution for arrival and exponential distribution for service time. D is to indicate deterministic or constant distribution. K is to indicate Erlang distribution. G is to indicate general dependent distribution. And I indicates general independent distribution. Symbols used in place of C are 1. which represents one server, or S, which represents multiple or more than one servers. Symbols used in place of D are infinite. Infinity means infinite population allowed in the system. Or N means finite population allowed in the system. Symbols used in place of E. They are different service disciplines, like FIFO, LIFO, SIRO, or priority. Based on these symbols, there are various types of queuing models. M1, infinite, FIFO. It means Poisson distribution for arrival, exponential distribution for service time, one server, infinite capacity of the system, and service discipline is first in first out. M1N, FIFO. It means Poisson distribution for arrival, exponential distribution for service time, one server, finite capacity of the system, and service discipline is first in first out. MS, infinite, FIFO. It means Poisson distribution for arrival, exponential distribution for service time, multiple server, infinite capacity of the system, and service discipline is first in first out. MEK1, infinite, FIFO. It means Poisson distribution for arrival, Erlang distribution for service time, one server, infinite capacity of the system, and service discipline is first in first out. This way, different combinations can be made to make different queuing models. Let us understand one queuing model in detail. M1, infinite, FIFO. It means Poisson distribution for arrival, exponential distribution for service time, one server, infinite capacity of the system, and service discipline is first in first out. In this model, the average waiting time per customer in the system or WS will be the average waiting time per customer in the queue or WQ will be the average number of customers in the system or LS will be the expected number of customers in the queue or queue length or LQ will be the degree of utilization of the system or traffic intensity will be the probability that the system would be idle is 1 minus degree of utilization. Let us take an example to understand this model. At a clinic, a doctor attends 15 patients per hour. The arrival rate of the patients at the clinic is 10 patients per hour, which is exponentially distributed. The expected waiting time per patient in the system would be 0.20 hours. The expected waiting time per patient in the queue would be 0.14 hours. The expected number of patients in the system at any time would be 2 patients. The expected number of patients in the queue at any time would be 1 patient. The degree of utilization of the system or traffic intensity would be 0.67 or 67%. The probability that the system would be idle is 0.33 or 33%. In the end, let us understand about the queuing psychology and its impact on queuing theory. Queuing theory actually ignores one very important aspect of queuing: how customers feel while waiting. Queue psychology is the study of people's perceptions of and responses to queues. Queuing experts have determined that unoccupied time feels longer than occupied time. Unexplained waits are perceived as longer than they really are. Queue psychology says that it is not the length of the line or the wait that matters most, it is how people feel while waiting. So, the waiting areas are designed to make waiting feel better. This is all about the queuing theory.